Good morning, all of you. My name is Shivani Khare. Today we are going to discuss acoustic phonetics. That's the topic of linguistics. Phonetics has been defined as the science of speech sounds. It is a branch of linguistics and deals with the sounds produced by human beings in their speech behavior. In speaking and listening, a complex of activities is involved. There is the production of a speech which is the result of simultaneous activities of several body organs. Phonetics has three major branches. First one is articulatory phonetics, second one is auditory phonetics, and third one is acoustic phonetics. Our topic is acoustic phonetics. What is acoustic phonetics? Acoustic phonetics is the study of physical properties of a speech and aims to analyze sound wave signals that occur within a speech through varying frequencies, amplitudes, and durations. One can analyze the acoustic properties of a speech sound is through looking at a waveform. Pressure changes can be plotted on waveform which highlights the air particles being compressed and rarefied, creating sound waves that spread outwards. A turning fork being stuck can provide an example of pressure fluctuations in the air and how the air particles oscillate, move in one direction rhythmically when we perceive sound. So, acoustic phonetics is the study of acoustic characteristic of a speech. Speech consists of variations in air pressure that result from physical disturbance of air molecule caused by the flow of air out of the lungs. This airflow makes the air molecules alternately crowd towards the move apart or oscillate, creating increases and decreases respectively in air pressure. The resulting sound wave transmits these changes in pressure from the speaker to hearer, and sound waves can be described in terms of physical properties such as cycle, period, frequency, amplitude, and these concepts are most easily illustrated when considering a simple wave according to pure tone. A cycle is a sequence of one increase or one decrease in air pressure, and a period is the amount of time expressed in second or milliseconds that one cycle takes, and frequency is the number of cycles in 1 second expressed in hertz. Increase in frequency usually results in an increase in perceived pitch. Amplitude refers to the magnitude of vibrations, with larger vibration resulting in greater peak of pressure, greater amplitude, which usually result in an increase in perceived loudness. Unlike pure tones, which rarely occurs in the environment, speech sounds are complex waves with combinations of different frequencies and amplitude. However, as first stated by French mathematician Fourier in 1768 to 1830. Any complex waves can be described as a combination of simple wave. A complex wave has a regular rate of repetition known as fundamental frequency f0, and changes in f0 give rise to differences in perceived pitch, whereas change in number of constituent simple waves and their amplitude relations result in perceived differences in timbre or quality. So Fourier's theorem enables us to describe speech sounds in terms of frequency and amplitude of each of its constituent simple waves. Such a description is known as the spectrum of sound. A spectrum is usually displayed as a plot of frequency versus amplitude, with frequency represented from low to high along the horizontal axis and amplitude from low to high along the vertical axis. And then, what is the relationship between this frequency versus amplitude? The frequency, that's pitch, and amplitude, that's loudness or intensity of a sound, can be analyzed on a waveform. Frequency can be calculated through the number of cycles on a periodic waveform with a repeating pattern. The higher the number of cycles per second, the higher the frequency and perceived pitch. Frequency is usually expressed in hertz, that capital H and Z. Then analyzing the amplitude of waveforms tells us how intense or loud a sound is and how much the air particle deviate. It is conventionally expressed in decibels, a small d and capital B. This is the relation between frequency and these are the 12 vowels of American English that spoken by 48 adult female, and F1, that's loudest speaker, that's speaked highly intensely by, that's shown in black color, and white, F2 in gray, that's uh, uh, that's shown low intensity. Then sine waves versus complex waves. Sine waves are waveforms that have very simple, regular repeating patterns. The number of cycles in the waveform, the number of complete repetition in the period waveform reflects the number of times the vocal cord have opened it within the time frame and displayed. This is known as fundamental frequency f0, which is measured in hertz. A frequency of 200 Hz means that there are 200 complete cycles per second within the waveform. So 200 times the vocal fold have opened it. In reality, most speech sounds waves have a rather complex pattern and are known as complex wave. These are made up of two or more simple sine waves and the fundamental frequency, and can also be calculated on complex waveforms by counting the number of cycles per second on waveform. This is the simple sine wave diagram shown time, frequency, and amplitude. This is the oscillogram where Hindi word peeth and pooth are spoken, and the stress on peeth is louder. That's shown in blackish color, and pooth in simple way it's spoken, and its intensity is shown very lightly. This is the diagram of sine and complex wave sound waves. Above one is the simple sound wave, and second one is complex sound waves diagram. Then what is the difference between periodic versus aperiodic sound waves? Sine and complex waves are periodic, meaning their cycles are regular and repetitive. The type of speech sound that would appear as a periodic sound wave are voiced sounds, such vowels or nasals. Since such sounds have regularly repeating waveforms, they can also be decoded through Fourier's analysis, which break down the components in waves. This type of graph is called a spectrogram, which does not measure time. Instead, the x-axis measures frequency and y-axis represents the sound pressure level. Then the fundamental frequency peak harmonics occur at evenly spaced integer multiples. Harmonics are known as the natural resonance within the vocal tract, and which are amplified frequencies on the spectrum. This corresponds to each peak. Speech sound can also be aperiodic when analyzing them acoustically. Then periodic and aperiodic waves, that's regular. Periodic is regular and repetitive, and aperiodic is not regular and repetitive. Then spectrogram. Another way to analyze the sound acoustically is through looking at the spectrogram. They provide much more complex information than what we can see on a waveform. Similarly to waveforms, time is displayed on x-axis, but y-axis measures the frequency of sound. Amplitude amplitude is represented by the darkness and acoustic energy. The louder the sound, the darker it appears on a spectrogram and is therefore more intense. And spectrograms allows us to see the high frequency energy that comes with aperiodic sounds. Then spectrum of sound, that's the relationship between amplitude that displayed in dB, and the frequency that's in hertz at that, amplitude in decibel. Then transient versus continuous sounds. Transients are the form of aperiodic sound. It is the sound that builds up pressure behind a closer and then has a sudden burst release which shows up as a spark on a waveform. When a spectrogram, the closure shows up as a blank space before a dark vertical band of acoustic energy to represent the release. A typical transient sound would be a plosive, such as pa and ba in the English sound system. Continuous sounds are another form of aperiodicity, like a voiced vowel sounds. This would shows shown up as an irregular random pattern on the waveform on the spectrogram. This would be represented by high frequency acoustic energy, which is dark and intense and therefore has high amplitude. This is a typical of many voiceless fricatives such as ha and sha in English sound system. Then voicing on a spectrogram, voiced sounds are periodic signals. A fundamental frequency can be calculated due to regular opening of the vocal fold as they vibrate on a waveform. This would be highlighted by a periodic sound wave. On the spectrogram, there are two specific usual elements to look out for and which resembles a voiced sound. The first is the vertical striations. They look like vertical wavy lines on the spectrogram, which correspond to this opening of the vocal fold and when air flow through them every time. The other usual clue is the dark horizontal band, which are typical of vowels, approximates, and nasals. They are called formants, and which are the natural resonances of the vocal tract. Earlier, they were described as harmonics. The size and shape of the vocal tract can be modified to allow these formats to vary. This can be done by changing the tongue position, lip position, etc. And this is the spectrographic representation of Hindi word peeth and pooth, articulated by an adult male speaker in JNU language lab. And here the lightness and darkness represent the intensity of the words, and x-axis represent time and frequency, y-axis, and this is three dimensional representation. In conclusion, the physical properties of a speech sounds from the domain of speech sounds. The latter are the composed of such physical characteristics as nasality, obstruction or friction of air pressure, sibilant, and the latter quality, loudness, amplitude, and turbulence of airflow, and these properties can acoustically be recognized and analyzed. From a linguistic point of view, a detailed description of a speech sounds in terms of their frequency, in addition to amplitude and duration, can elucidate the factors that shape sound, categorize, and determine phonologically process both within and across languages. In addition, acoustic phonetics analysis may uh, serve to quantify uh, atypical speech patterns produced by non-native speaker or speaker with specific speech disorder. Thank you very much for this is the work consulted, and thank you very much for listening. Thank you.